Reservations in two-way slabs by means of yield line. This video will deal with the cases 26 to 30. This is about concrete slabs who are on two opposite sides fixed and the two other sides simply supported. And case 26 is about a rectangular hole with certain conditions on it. Let's look at case 26 now, but before we do that, we will first calculate the maximum bending moment of the slab without a reservation in it. So it's valid for cases 21 to 25. First, we draw the negative yield lines because it is fixed, so you have a negative yield line there. And on the bottom, you have negative yield line. We use the 60 30, 45-degree rule. So we draw from the cross sections of the two axes of rotation. From this point on, over an angle of 60 degrees, we draw the yield line. We do the same in the opposite corner. And then we connect the two intersections. So now we have the yield lines of the slab in ultimate load, and each part of the slab can now move as in a mechanism, and the axis of rotations are the four sides of the slab. Some geometric characteristics, S1 is indicated here, and with the cotangents rule, it can easily be calculated as A times square root of 3 divided by 6. S2, of course, it's half A, the side A, because of the symmetry. S3, again with the cotangents rule, and S4 is equal to S2. Now, in general, when we have the yield lines, the positive yield lines are of a value m, negative yield lines are of a value 1. It's not necessary that m is equal to m1, but because in most cases we assume that the reinforcement in the bottom of the slab is the same as in the top of the slab, so we choose for our calculations to use m1 equal to m. But it's not really necessary. You can easily use m1 as m times the proportion of the area in the top reinforcement to the area in the bottom reinforcement. Now we can calculate the work done by the external forces. This is, of course, for the triangles, we got S1 times A, 3 times A, and the mean deflection is delta over 3. And for the rectangular portion, we got this, which is B minus S1 minus S3 times A, and the mean deflection delta over 2. To substitute the different variables, we get this formulation. The work done by the internal forces is M1 projected on this axis, so it's M1 times B times delta over S4. And this is M projected on this axis, so M times B over the angle delta divided by S4. Further on, we have M times A divided by S3, M times A divided by S1, and we have M times B divided by S2, and M1 times B divided by S2. Substituting the variables, we get this formula. When E is equal to D, we can get M, and M is then equal to what is written here. It's only a function of the load and the geometric characteristics, and we call this value, we call it M0, meaning that this is the maximum bending moment without a reservation in the slab. Now let's check this. For a square slab A is equal to B. We substitute in the formula and we have 2a squared over 37, which corresponds well with literature. For an existing slab where there's no reservation in it, then the reinforcement is equal to the reinforcement that is needed for M0. The bending moment is Q times C. C is a factor only depending on the geometric characteristics, and Q is the ultimate limit load. M0 is Q0 times C0. And then you can easily see that Q over Q0 equals C0 over C and equals M0 over M. So for all the further calculations, we will use EX. It's E divided by delta Q, and dx d divided by delta M. So it means when E is equal to D, then M is Q times EX over dx. And then we define bearing capacity as 100 times the ultimate limit load divided by the ultimate limit load without the reservation in the slab, or 100 times M0 divided by M because of this relationship. Now let's go to case 26. Let's go now to case 26 with a rectangle reservation positioned on a distance d4 and d3 from the edges of the slab. We know from the geometry what S3 and S1 is and what S2 and S4 is. And because it's a two-way slab, we know that B, the distance B, must be between A and 2A. The horizontal position of the reservation is such that the right-hand side of the reservation always between the yield lines on the left-hand side and the yield line on the right-hand side. So it means that D2 plus D4 must be smaller than this point, which is B minus S3, but must be bigger than S1, which is this point. Also, D4, of course, must be smaller than S1, and the tip of this reservation must be on the left-hand side of this slope of this yield line, the slope of the yield line, which is S1 over S4. So D4 must be smaller than S1 over S4 times D3. Then we got the vertical position. In the vertical position, D1 plus D3, D1 plus D3 must always be bigger than S4. It means that this side of the reservation is on the other side of the horizontal yield line. And D3 is smaller than S4, so this side of the reservation is always on this side of the horizontal yield line. Now we have the different conditions. By putting in the values of S1 up till S4, we got those conditions. Let's give an example of reservations that comply with those conditions. For instance, a reservation like that complies. A reservation like this complies too. It's on the limit, but it's okay. This is also right. This side is between this and this yield line, and top and bottom are on both sides of the horizontal yield line. Same here too. This yield is now on the limit there. This side is also on the limit, and it is in between the or on both sides of the horizontal yield line. So we can continue up to that. So these are all the different reservations that can be made in type 26 reservations. An example of which is not good, this reservation is not good because the right-hand side is on the wrong side of the yield line. First of all, we will look at some other parameters to calculate the work done by the external forces. We have to define x1, and x1 is the distance where the reservation cuts the yield line. So it's not d4. d4 is this portion, x1 is this portion. So it's from there to there. X2 is the same, is the distance to the yield line at this side of the reservation, and Y1 is like it is indicated here. You see easily X1 is according to the slope of the yield line is the square root of 3 divided by 3 multiplied by B3. X2 is the same as Y1 and it's on the same slope. And Y1, of course, it's A minus D3 minus D1. To calculate the work done by external forces, we need deflections. The horizontal yield line is the maximum deflection delta, and the others are proportional to delta. So this means that if you use the rule of proportion, that for instance, for this slab, the maximum deflection, when this is 0 and this is delta, it will cause delta times d3 over s4. The same happens for this piece of slab. There it's 0, here it's delta, so at the distance d4, the deflection is delta d4 divided by s1. And of course, the same happens here for y1. Now we have all the parameters to calculate the work done by the external forces. And first we start with the orange zones. This is the summation of all the rectangular portions. And we see, for instance, that for this portion, we have d4 times d1 and times the maximum slope, which is delta d4 divided by s1. Then we have d3, this portion, d3 times d4 plus d2 minus x1. So we only need this length, and this is multiplied by d3 over s4, which is the maximum deflection on this point when this deflection is delta. Then we got the bottom rectangle here. We have let's say y1 times this distance, which is d2 plus d4 minus, of course, x2. So that's this portion. And the maximum deflection there is y1 divided by s2. And now what's left is this rectangular, which is a times b minus d4 minus d2 minus s3. And the mean deflection is 1/2 because it's all about rectangulars. Now we look for the triangles, which is the green part. Then we see for the green part, this is easy, it's a times s3. And then we have the two left corners, which is this value x1 times d3 divided by 2 because it's a triangle. And the maximum deflection is x1 divided by x1. Then we go to the other one, which is d3 times x1 divided by 2. And the maximum deflection of this portion is d3 over s4. The same we do at the bottom, the same system. And we take the mean deflection of triangles, which is delta over 3. Now this is getting a little bit difficult to write it all in one formula, so we cut the formula in a portion which we call h, and then we can write Ex is then equal to this formulation. Then next we will calculate the work done by the internal forces, which gives us the yield line, negative yield line here. It's projected to or projected on the axis of rotation. It gives you m times b divided by the angle of rotation, which is delta over s4. Then we got this yield line here, negative yield line, is b divided by S2. Then we can have this yield line, which is A, is projected on this axis, A divided by S3. And we can have this yield line projected on this axis, which gives this yield line, which give you in total length of B minus D4 minus D2 divided by S4. And on the other side is the same, it's similar. It's B minus S4 minus S2 minus S3. But no, S3 is included because it's going from this to this, divided by S2. And then what is left are those yield lines, and which is easy. It's x1 divided by s4, and d3 divided by s1, x2 divided by s2, and y1 divided by s1. Then we can substitute the different variables, and we arrive at this formulation. We know that the bending moment is then the load times EX divided by DX. And we know that there is a limitation on this type of reservation, because otherwise the formulas that we have constructed now for E and D will not be valid. This was the horizontal limitations, and this is the vertical position. Now we have everything in place to calculate the effect of reservation in a slab. For instance, we have here a slab 6 by 9 meters, and there's a reservation in it of 1.2 times 4.2, and is situated on in this location. The floor or the slab is loaded with 2 kilonewton per square meter as floor finish and 5 kilonewton per square meter as live load. Its depth of the slab is 180 millimeters, and the concrete covers 40 millimeters. What is the needed reinforcement? We first calculate the load in ultimate limit treatment, and it is 1.35 times the permanent load plus 1.5 times the mobile load, and it gives us 16.3 kilonewton per square meter. We fill in the different parameters. We check first the horizontal position, and with D2 and D4, D2 was 4.2 meters, D4 0.6 meters, so it's 4.8, and we check this if the limit is okay, and this is fine. The other condition for D4 was this, and this is also fine, and the other condition on D4 was this, and that's also fine. For the vertical position, D1 plus D3 must be bigger than 0.5a. It means 3.6 bigger than 3, so this is okay. And this is also okay. Now we can further calculate the other parameters as S1 and S3, S2 and S4, Y1 and X1 and Y2. These are now the different parameters. The maximum bending moment, assuming of course that the reinforcement on top is equal to the reinforcement on the bottom, it means that we choose it now to make it the same. Then H, the intermediate parameter, can be calculated. Ax, Bx, and the bending moment is then 19.7 kilonewton meter per meter. Now we will transform the bending moment into reinforcement, and the lever arm is 132 millimeter. The needed reinforcement is 1.1 times the bending moment divided by the lever arm and divided by the yield strength of the reinforcement, and that leads us to 419 square millimeter per meter, or diameter 8 every 120 millimeters will be fine. And this reinforcement is of course top, bottom, x direction and y direction. You can also choose for diameter 10, then you use here diameter 10, then you change the lever arm and you arrive at 426 square millimeters per meter, and that's diameter 10 every 175 millimeters. We can now have another example, an example of an existing slab reinforced in two directions, and the top reinforcement is equal to the bottom reinforcement, but we do not know the quality of the concrete or the reinforcement that is put in it or the load where it was calculated for. Now, in this existing slab, they want to make a reservation of 1.8 by 0.5 meters to put some cables through it. The question is this possible? Can we do that? First, we can calculate the maximum bending moment when there is no reservation in it. So, and we divide it by the load, because we do not know the load, and we have on the right-hand side of the equation only an element that is depending on geometric characteristics. You can calculate it and it says 1.243. The maximum bending moment with the hole, we use the formulas of the previous slides, is 1.247. So it means that this is almost equal, which means that the bearing capacity is 100%. So making a reservation of this size, of this location, will not affect the total bearing capacity of the surface that is left over after making the reservation. Of course, we assume that all reinforcement is properly anchored. Let's have an example of how you can manipulate or how you can work with those equations of the previous slides. Suppose that we have a concrete slab where this side and this side is fixed and the other two sides simply supported. And on this slab, we want to make a reservation for cables or for ventilation. And we are wondering on this position, what is the effect of a reservation going from this side to this side? So that means that alpha 1, that's the width of the reservation, is 0.1 times A. And that's 0.6 meters, something more than half a meter. Alpha 3 is the position, but it's in the middle of the slab. So alpha 3 is 0.45 and alpha 4 is 0 because alpha 4 starts there. And the length of the reservation varies from 0.209 times A till alpha minus 0.29. It is this situation and this situation. So now we want to know what is the influence on the bearing capacity of this type of reservation. We will check if case 26 is applicable. This is the horizontal position. We do not know because we use it as a variable in our problem, the B and A. So the alpha, which is B over A, we do not know, and alpha 2, that is the parameter that we are looking for. So this is a condition on alpha and alpha 2. This is fulfilled, and this is also fine. In the vertical position, this is also checked. This is okay. So it means that we are left over with this condition to have a case 26 rectangular door. This must be true. To give you an example, when alpha is 2, because alpha is between 1 and 2, when alpha is 2, then you have this kind of reservation. When alpha is 1.5, you see that this is the influence, and alpha 1, this is the case. So this is why alpha 2 changes according to this rule. Now we can calculate the bearing capacity for different values of alpha and different values of alpha 2. So in the vertical axis, it's the bearing capacity. Horizontal, it's alpha 2, which is the length of the reservation in our problem. For instance, for a square slab, when alpha is 1, this is the only valid line because after this value of alpha 2, the Alpha 2 must be between this range, and you see if alpha is 1, then you have 0.73. So after that, the formula is not valid anymore. That's why I put it to 0. So now you have all those lines for alpha from 1 to 2. We see that in almost all cases, the bearing capacity is below 100%. So it means for this type of reservation, we are lowering the bearing capacity of the slab. Let's have an example, for instance, for the black curve, alpha is 1.5. So here's the black curve. We will see that in this point, that for alpha equals 1.211, which is this limit, 1.5 minus 0.289 gives you a bearing capacity of 92.5. So you lose about 8% of the bearing capacity for a reservation made like this. For another example, for alpha 2 equal to 0.75, gives you this reservation. Then the bearing capacity only lose something like 4%. And then the third point, when you make a reservation like that, there is almost no loss of bearing capacity at all. It's about 100%. So this type of reservation leads to a loss in bearing capacity of a maximum of, we have made all those graphs, so a maximum of, let's say, 8%. So that's how you can deal with the formulas to help you choose to make the right reservation. Of course, when you look at those three pictures, you see immediately that their yield lines are almost not cut except this very small part. So that means that you have 100% of the bearing capacity. Here you cut a yield line, and here you cut also this yield line. So you should avoid cutting yield lines. Now, in this problem or example, the bearing capacity is more than 100%. That's what we want. We do not want to touch the existing bearing capacity by making a reservation. Well, PC is bigger than 100 on the condition that alpha 2 is smaller than alpha 2 max. And you can easily calculate with the formulas alpha 2 max by making the bearing capacity equal to 100, and you solve it for alpha 2, and we call it alpha 2 critical. And then you have this equation. It's of course an equation of alpha. Now you can make a graph on the y-axis alpha 2 critical, and on the x-axis you have alpha. But we know that alpha 2 has a limitation, which is also a function of alpha. So now we can have, for instance, the upper limit, call it E2, but it doesn't matter. Call it the upper limit, which is this red line. That's the upper limit. It's a function of alpha. And alpha 2 has also a lower limit. Okay, this is constant. So this is the red line at the bottom. So every value that we have for alpha critical must be between those two lines. Otherwise, it's not valid. Otherwise, we do not have a reservation in the slab that fulfills case 26. And then we plot this formula alpha 2 critical, and we see that it's almost like that. So only this part is valid. So for alpha bigger than here 1.244 BC, the bearing capacity is smaller than 100%. We can enlarge this part in function of alpha, and do it again alpha 2 critical. And we see, for instance, for this point, when alpha is 1, a square slab, and alpha 2.4 times A, or the length of the preservation is A times 0.4, then we are here, and then you see we have more than 100%. Another example is this point here, we have 100%. And when you take an example here with the alpha is equal to 1.2 and alpha 2 is equal to 0.4, then you see that you have a loss in bearing capacity. So the area that you are interested in is this small area. Otherwise, it's always a loss in bearing capacity. So this small triangle is okay, and all the others you have a loss in bearing capacity.